In today's lecture, we're going to be talking more about division as well as more about powers. So these are both topics that we've already sort of covered, but not in very much detail. And we're going to go through and figure out in gory detail how these things all work. So more modular division. This is one of the harder topics we're going to be dealing with, but it connects together some of the other ones we've already covered both in this part of class as well as the beginning. So now we're sort of at the end of week 8. We're going to start seeing how some of the tools that we've been putting together, how some of the tools we've been learning throughout the class all get put together. And so we only have 4 more weeks of class. And so we're starting to see some of the payoff of all the stuff that we did at the beginning. So let's go on. So let's recap. What is modular division? Well, it's just division in modular arithmetic. So the opposite of multiplication. And the way it normally works is you just write a ratio x over y is equivalent to z mod n. If z is the unique number, and unique here is important, you can define it without uniqueness, but we're not going to do that since life gets really complicated when you do. It's the unique number in mod n arithmetic such that y times z is congruent to x. So a couple of examples. We did a bunch of these last time, but just to make sure we're all on the same page. Oh, we have a chat question. I think a big fear about coordinating is that you'll mention your topic and someone might take it. Well, I mean, it's one of those problems where you have to trust each other. How well do you know your classmates? Yeah, anyway, so 3/4. So that's congruent to 2 mod 5 because 4 times 2 is equivalent to 8 is equivalent to 3. And this is true for only 2. Is only true for 2. For 2. Let's give another one while we're here. 3 divided by 4 mod 6. This, on the other hand, is undefined because 4z mod 6 is always even and can never be 2. It can never be 3. Right, and the way we notice this is because we know that 4 and 6 are not relatively prime. And you'll see that this ends up giving you problems when you have, because you only end up with multiples of 2. And lastly, 2 divided by 4 mod 6 is also undefined, because it turns out there are 2 answers to this and not just one. The link is in the upper right corner of the screen. So bastion.ydvu.net. But anyways, this is undefined because 4 times 2 is congruent to 8, which is congruent to 2 mod 6. But at the same time, we also have 4 times 5 is, oh wait, I did that one wrong. Which one is it? So 4 times, oh, no, that's right. 4 times 5 is congruent to 20, which is also congruent to 2 mod 6. Okay, so division is only properly well-defined for the purposes of this class when there's a single unique answer. In other classes, you might define it slightly differently. So if you ever take the time to actually take a proper number theory course, you can define it the other way as well, but we're not going to. Is there an alternative way to solve modular division? Yes, that's the whole point of this lecture. So last time I gave you a sort of brute force way of solving modular division, right? So you have to just write out all the things and then try to figure out what the reverse is. In today's class, we're going to talk about a way to get modular division without having to go through this process of checking everything and then finding the reverse. And the way we're going to do that is the Euclidean algorithm. So remember, like we learned the Euclidean algorithm like back in week 2 or something. I don't remember when exactly we learned it. But it turns out that we can use the Euclidean algorithm for solving a reciprocal. And if we can solve for a reciprocal, then we can solve for division, right? So what do we need? So if we're trying to find the reciprocal 1 divided by 7 mod 11, well, what we're really saying is we need 7 times x, for some x, a number, to be congruent to 1 mod 11. right? That's all we really mean. So it's the opposite of multiplication. Well, what is that? So, or this also means, so this is where it becomes important. So earlier we were only working in modular arithmetic, and so we could just keep on using, so it doesn't really matter to, I wasn't super careful with equals and equivalent signs, but now we do need to be careful because we're going to be working in simultaneously modular arithmetic and normal arithmetic. So, or this also means 7x is equal to 11y plus 1, where x and y are integers. Why is that? Because the whole point of modular arithmetic is two numbers are the same when you go around the circle any number more times or fewer times. And so going around the circle in mod 11 is adding or subtracting a multiple of 11. Which means that the statement 7x is equivalent to 1 mod 11 is basically the same as the statement 7x is equal to 11y plus 1, where x and y are both integers. But we can rewrite this, right? So we can rewrite this as 1 is equal to 7x minus 11y. And now all of a sudden this ought to look a bit more familiar, because what we have now is we have a combination. So this is a combination of 7 and 11 equal to 1. And we now have to solve that. So let's go ahead and solve that. And the way that we learn how to solve this, so this way back when we were measuring cups, this was on the midterm. I think people did pretty well on that question, actually. So is to use the Euclidean algorithm. So 11 is equal to 7 times 1 plus 4. 7 is equal to 4 times 1 plus 3. 4 is equal to 3 times 1 plus 1, and 3 is equal to 3 times 1. And you notice that the GCD is of 7 and 11 is equal to 1, which is good because that means we can do division. So you can only do division whenever the GCD is equal to 1 and they're relatively prime. Okay? And so then we can conclude, well, we just need to write 1 as a combination of 11 and 7. So what's that? Well, 1 is equal to 4 minus 3. And 1 is equal to, replace the 3, 4 minus 7 minus 4. Excuse me. So then 1 is equal to 4 times 2 minus 7. And 1 is equal to, replace the 4 with 11 minus 7 times 2 minus 7. So then 1 is equal to 11 times 2 minus 7 times 3. And now all of a sudden, we've written 1 as a linear combination of 11 and 7. So now the question is, now we've been doing all this in ordinary arithmetic, right? But now, we want to answer in modular arithmetic flow. So what should we do now? Can we just go back and forth between ordinary and modular arithmetic? Well, to answer that question, let me point out that if two numbers are the same, so if two numbers are just the same in ordinary arithmetic, and then you divide that number, the same number, twice by the same thing, and you find the remainders are going to be the same as well, right? And therefore, because we know the left-hand side and the right-hand side of this equation are exactly equal, we can just divide and take the remainder mod 11 on both sides. And so really what we mean by that is you can then convert this into a statement in modular arithmetic. So 1 is equivalent to 11 times 2 minus 7 times 3 in mod 11. And this is of course true for any mod, because with equal signs mean that the two sides are actually exactly the same. And so if you have the same thing and you do the same operation to the same thing twice, you get the same answer. So you can do that conversion. And then once you've done that conversion, well, you notice in mod 11, what is 11? Okay, yeah, we are getting a couple zeros in chat. So So this is equivalent to saying 1 is equivalent to 0 times 2 minus 7 times 3, mod 11. Okay, so 1 is equivalent to 7 times minus 3, right? And, well, what else do we know? What is minus 3? Well, minus 3 is just 8. So 1 is equivalent to 7 times 8, mod 11. Well, now we can conclude that 1 divided by 7 is equivalent to 8, mod 11. Okay, so this is another way of computing. This allows you to compute the reciprocal. And importantly, this doesn't require us to list out the entire multiplication table. Instead, we just use the Euclidean algorithm to solve for what the reciprocal was. And then once you have the reciprocal, you can, of course, then just multiply back through, which we'll do in a moment. Would it be wrong if you left it as minus 3? So what I will say is that for the purposes of future quizzes and exams, you can leave it as minus 3. But if you're going to leave it as a minus number, it also has to be in the smallest possible form. So you have to choose so like if you did minus 14, I would probably consider that wrong. But if you did minus 3, I would accept that on future things. So you have to be careful because you don't want to confuse yourself. So the minus 3 is 8. But now that we've already assessed that, you are allowed to do minus 3. So the two numbers are the same. If the GCD isn't 1, does that mean it isn't well defined? Yes, that is exactly what it means. If the GCD isn't 1, then you can't, remember, if the GCD, what things can you find as combinations? You can only find as combinations things that are multiples of the GCD. And so therefore, if you're trying to find a combination equal to 1 and your GCD is 2, then that is just impossible. And so that's sort of the point here is that, and this is why actually, well, one of the reasons why. This is one way of thinking about why you do need the two numbers 7 and 11 to be relatively prime. Because if they're not relatively prime, then you don't have a reciprocal. Okay, enough of me shouting at y'all. Let's have you all try it out. So what's the reciprocal of 1 divided by, or what's the reciprocal of 1 over 9 mod 13? Now, of course, there are two ways of solving this, but hopefully we can get you all to solve it using the Euclidean algorithm, since you guys have a ton of experience with that now. And let me go ahead and just give you all the setup so that I can repeat it again. So what you need is you need 9x is equivalent to 1 mod 13, which is the same as saying 9x is equivalent to 1 plus 13y. Oh, sorry, not equivalent, equal to. And I'll give you all a moment because this one does take a little bit longer. And while you're working, I'll just go ahead and repeat again. This is why, one of the reasons why I said that you guys should practice all these other tools that we did earlier in the class. Because the Euclidean algorithm earlier on, so like for the midterm, for some of the earlier quizzes, that was just a problem in and of itself, right? On later quizzes and on the final exam, the Euclidean algorithm might not even be its own question. It's just like one small part of like another question that you have to answer. Let's see, we got an answer 0. I'm not sure how you got 0. Remember, you can always double check your answer by multiplying it back and seeing if you get the right answer. So whatever answer you get, if you multiply by 9, you should get 1 in mod 13. And 0 times 9 gets you 0 in mod 13, which is not equal to 1. Okay, so we're starting to get answers. We got one or two answers. Well, while you guys keep on working, let me just follow through as well. So 1 is equal to 9x minus 13y. So you need a combination of 9 and 13. So, well, 13 is equal to 9 times 1 plus 4. 9 is equal to 4 times 2 plus 1. 4 is equal to 4 times 1. So, therefore, you have 1 is equal to 9 minus 4 times 2. And 1 is equal to 9 minus 13 minus 9 times 2. So 1 is equal to 9 times 3 minus 13 times 2. Okay, so we have some combination, and we can rewrite this in modular land as 1 is equivalent to 9 times 3 minus 13 times 2 mod 13. But of course, then that piece goes to 0. Just 1 is equivalent to 9 times 3 mod 13. And that, of course, leaves us with 1 over 9 is equivalent to 3 mod 13. Okay, so it seems like people got that. A little bit slow, but like these are problems where you just have to use the Euclidean algorithm over and over again. And once we have that, we can do division. So how do we do division now? Well, step 1, check to see if the two are relatively prime, because if they're not relatively prime, then the division is ill-defined. So for example, 7 divided by 9 mod 13. Well, what is the GCD of 9 and 13? Well, if that's equal to 1, then it's great. If it's not equal to 1, then you're in trouble. And well, I mean, or then you just can't do that division uniquely. But of course, so there are several ways of checking for relative primeness. You can either use the Euclidean algorithm or you can use factoring. But it may make sense to use the Euclidean algorithm because if you can solve for the reciprocal, then you need the Euclidean algorithm anyway. So this was from the previous slide. We know that 1 divided by 9 is congruent to 3 mod 13. And then step 3, well, we just multiply back through. X times 1 over y mod n. So that would be 7 times 1 over 9, which is equivalent to 7 times 3, which is equivalent to 21, which is equivalent to 8 mod 13. Okay, great. So let's try it out again. What about 8 divided by 9 mod 23? So one of the things you're going to have to start worrying about is I'm still using relatively small numbers, but you'll notice they're getting bigger. And there will be some examples of numbers that are far too big for you to actually list out everything, and you will have to use the Euclidean algorithm to solve for it. Let's see, we got 1, none of the above. And we got a C for 6. Okay, well, let's start going through it. So what are the various steps? Well, let's start with the Euclidean algorithm. So 23 is equal to 9 times 2 plus 5. 9 is equal to 5 times 1 plus 4. 5 is equal to 4 times 1 plus 1. 4 is equal to 4 times 1. So GCD of 9 and 23 is equal to 1. So that's good. And then we need to solve for 1 over 9. Well, what do we get? 1 is equal to 5 minus 4. So 1 is equal to 5 minus 9 minus 5, which is equal to 5 times 2 minus 9. So 1 is equal to 23 minus 9 times 2 minus 9, which is equal to 23 times 2 minus 9 minus 5. Okay, and we can go from that and go into modular land, the mod 23 land. So 1 is equivalent to minus 9 times 5 mod 23. And therefore, we know that 1 over 9 is equivalent to minus 5 mod 23. And so 1 over 9 is equivalent to, you can say it's equivalent to 18, or you can say it's equivalent to minus 3. They'll both be acceptable for now. And then lastly, you multiply it back through. So what's 8 times 1 over 9? I'm actually going to do minus 5 because it's a little bit easier to multiply. From the minus 5, mod 23. So 8 divided by 9 is equivalent to minus 40. Mod 23. Well, you can add back through. So 8 over 9 is an equivalent to 6. Mod 23. And you can see that just by adding 46 to it. Okay, so it seems like everyone has gotten the hang of that. I have another 2. So we'll go through them relatively quickly because it looks like you guys sort of know what we're doing. So what about 7 divided by 216 mod 691? Okay, we got one answer of C so far. Let's see what a couple more people get before I start solving it. Oh, I didn't give you guys options, did I? Your early options. How are you guys getting C? I'm very confused how you guys got C without even knowing the options. Oh, yeah. Oh, I guess C was the answer last time. Yeah, so it probably is just catch up from last time. Okay, well, anyway, maybe the answer is C, but let's see. What is the answer this time, though? Well, let's solve it together. So let's see, 691 is equal to 216 times 3 plus 43. And then we get 216 is equal to 43 times 5 plus 1. And then 43 is equal to 43 times 1. So the GCD of 216 and 691 is equal to 1. So that's good. And now we just need to solve for that. So 1 is equal to 216 minus 43 times 5. 1 is equal to 216 minus 691 minus 216 times 3 times 5. So then 1 is equal to 216 times 16 minus 691 times 5. And 1 is equal to, and then from there, we just go straight into modular land. And that gives us 1 is congruent to, well, oh, sorry, I erased, that's times 5. So once we're in modular land, we have 1 is congruent to 216 times 16, right? Mod 691. So the right-hand term, the right side term disappears, 691 times 5. Okay, so what does that imply? It implies that 1 over 216 is equivalent to 16 mod 691. But if that's the case, then 7 divided by 216 is equivalent to 7 times 16, right? Which is mod 691, which is equivalent to 112 mod 691. So the answer here is actually A. And I am somewhat concerned that so many people put down C, because that suggests to me that some of you are that suggests to me that some of you are not actually solving it, but just going with whoever like solves it first. So be careful about that. Let's see. Is it easier to check if the two numbers are relatively prime right away, or is it easier to do the Euclidean algorithm to see if the GCD is equal to 1 or not? So that is, you have two ways of checking to see if the GCD is equal to 1, right? You have the Euclidean algorithm and you have factoring. And sometimes one will be faster and sometimes the other will be faster. It really depends on which method you're better at. For some numbers, if you're very familiar with primes, you can just stare at them and figure out the prime factorizations. But for other numbers, it's a lot harder. And there isn't a single answer I can give you for that one. Can you give us more time to solve? Okay, yeah. So I have one more here. So I'll give you a little bit more time and I will try not to rush. I think I just started that one because someone answered C really quickly. And so I thought you guys had were actually solving it. But I'll give you a little bit more time on the next one. So what about, and I'll give you the answers this time. So what about 10 divided by 183 mod 1521? Oh, and to continue answering the question about what's easier, factoring or checking using the Euclidean algorithm, one of the things you might, so figuring out that the GCD is actually equal to 1, that the greatest common divisor is equal to 1, would require a full prime factorization, which is often a little bit slow. But if what you're interested in is whether they're not relatively prime, then sometimes you can figure it out a lot more quickly. Like for example, if I gave you two even numbers, you immediately know that's not relatively prime, right? Because they're both divisible by 2. And so for certain numbers, you should be able to see it and recognize that they're not relatively prime. But for two arbitrary big odd numbers, it can be harder to figure that out. Also, what I just said a moment ago might have been a hint about this problem. So. Okay, it looks like a couple people are answering E. I'm going to wait until the number of responses hits, say, 20 before I move on, just to make sure that a decent number of y'all have made it. Okay, so remember what I said about some numbers being easier to check divisibility. It turns out that these two numbers are divisible, and there's an easy check. So one thing that you might remember is that you can check to see if a number is divisible by 3 by adding together the digits and seeing if the digits are divisible by 3. So notice that 1521 and 183 are both divisible by 3. Right? Because these digits summed up is 12, and these digits summed up is 6, 9. So those are both divisible by 3. So therefore, ill-defined. And if you wanted to, you could also use the Euclidean algorithm. But the Euclidean algorithm on this one is actually kind of painful. It's 1, 2, 3, 4, 5, 6 steps. But in this particular case, if you did recognize that both of the numbers are divisible by 3, then you wouldn't need to, because you already know it's not relatively prime. Any questions about that before we move on? Okay, great. So let's talk a little bit about one more shortcut you can do while you're doing division, which is sometimes you can also factor out the modulus. So what do I mean by that? Also, why doesn't this work for non-prime modulus? But you guys can answer that while I give a couple examples of this. So, and you can think a little bit about why it doesn't work. So let's say we had 5 divided by 10 mod 11, okay? So one way of doing this is you can solve this directly. So 11 is equal to 10 times 1 plus 1, and therefore you know that 1 is equal to 11 minus 10, and so 1 is congruent to 10 times, wait, did I do that? Just a moment. Oh, yep, it's congruent to 11 minus 10 times 1 mod 11. And therefore, you know that, which is 1 is congruent to 10 times minus 1 mod 11, which implies that 1 over 10 is congruent to minus 1 mod 11. And therefore, 5 over 10 is congruent to 5 times minus 1, which is congruent to minus 5, which is congruent to 6 mod 11. Okay, so you could do it the brute force way, but you could also notice that you can also change it. So for example, 5 over 10 mod 11 is congruent to 1/2 times 5 over 5. Okay, yeah, so you're just factoring it out. Mod 11, which is congruent to just 1/2 mod 11, right? Because 5 divided by 5 is equal to 1. And so then you can solve that instead. So 11 is equal to 2 times 5 plus 11. 1 is equal to 11 minus 2 times 5. So 1 is congruent to minus 2 times 5 mod 11. And so therefore 1/2 is congruent to minus 5 is congruent to 6 mod 11. Okay, so when you have fractions and you have a prime modulus, you can factor out fractions. Anyone want to give a guess as to why this does not work for non-prime modulus? It might sometimes work for non-prime modulus, but it will not necessarily work in general. And there's a deep reason for this, which you guys should be able to recognize. So what are the things that you can't always do in non-prime modulus? So what's special about a prime number as your modulus? Something to do with division, maybe? Yes, it is easier to divide. But what do we mean by it's easier to divide in the prime modulus? Yeah, so the GCD is always equal to 1, right? So in the prime modulus, you can divide by anything except for 0. And notice here, we divided by 5. And so if you're not working in the prime modulus, you might factor stuff out, but the things you're factoring out might be dividing by things that you can't divide by. And so when you're working with non-prime modulus, this might not work. And we'll see an example of that in a moment. Yes, so always relatively prime when you're in a, yes. Okay, so let's try that out. So let's find 7 divided by 70 mod 71. And so on the final exam, like on the midterm, I will give you the list of all the small primes. And so You won't have to memorize them, but it is good to recognize when small numbers are prime, because that can be really helpful in whatever you're doing. So let me zero that out. Someone is claiming that 71 is not prime. If you're claiming that 71 is not prime, please give a prime factorization of it. But yes, that is a very important thing to check. Like, very good instincts, but. Okay, so I will just go ahead and say that this is actually prime. So this is prime. So there are two ways you can solve this. And I should mention that just because you can factor things out doesn't mean you always want to factor things out. Sometimes it'll be easier when you don't factor things out. But let's just check both ways. So we know 71 is, so let's say we factored it out. So what we're trying to find is 1 over 10. And so, so that's equivalent to 1 over 10. And so 71 is equal to 10 times 7 plus 1, and 1 is equal to 71 times minus 10 times 7. So 1 is congruent to 71. Oh, sorry, the 71 disappears. So 1 is congruent to 7 times, minus 7 times 10. And so therefore we know that 1 over 10 is congruent to minus 7, which is congruent to 64. This is mod 71, of course. Notice that in this particular case, it actually doesn't help you very much to do the factor. Why is that? Because if you were to do this division without doing the factoring, sorry, this example actually isn't great for that. But another thing you might notice is, where was I? Yeah, so another thing you might notice is that this is also, another way of looking at this is is also 7 times 1 over 70 mod 71. And if you're going to get 1 over 70, well, you have 71 is equal to, 1 is equal 70 times 1 plus 1. And so 1 is equal to 71 minus 70. And so 1 is congruent to minus 70. Wait, did I do that right? Oh, yeah, yes, I did. So 1 divided by 70 is congruent to minus 1. And if you multiply this by 7, so then that means that 7 over 70 is congruent to minus 7, which is congruent to 64. Okay, so you can do it both ways. Sometimes one will be easier than the other. You just sort of have to recognize it. Both ways will work, but sometimes there will be a shortcut that will save you a lot of time. Okay, so the answer there was 64. And let's try to do one more. So let's do 7 divided by 70 mod 91. Okay, we're getting a few answers here. So as an aside, you won't get multiple choice questions on your exam. But if you were to ever get multiple choice questions, one thing you could do is you could just multiply these numbers back and then see if they see what answers they give. And I'm going to, so let's solve this a couple of different ways. So let's first solve this by factoring, right? So the question is, can you factor? Well, maybe. So let's say, so let's start by claiming that 7 divided 70 is congruent to 1 over 10 mod 91, and then 1 is equal to 91 minus 10 times 9. Okay, so the Euclidean algorithm is really easy here. So 1 is congruent to minus 10 times 9. So 1 over 10 is congruent to minus 9, which is congruent to 82. Okay, so a lot of people got that answer, but a few people got E. Could some of the people who got E explain why? Yes. So things go wrong here because list number is not prime. So list is 7 times 13, right? And so this actually is wrong. I mean, it's not wrong in that you don't get a answer, but notice that you get the problem where GCD of 70 and 91 is equal to 7. So we have multiple solutions. I'm not going to solve it, but another example is 4 times 70 is also congruent to 7 mod 91. And so this one and this one are both answers. And so the actual answer is none of the above because they weren't prime to begin with. So now this is one place where factoring might lead you astray. Because when you factor, you notice that 10 and 91 are relatively prime, but 70 and 91 aren't. And so this is why when you're not working in a prime field, in a prime modulus, things can go wrong. So 91 is not prime, and that is why things go wrong. So you have to be really careful whenever you're working with things that aren't prime. Okay, and with that, okay, that took a little bit long. No, the answer is actually none of the above. So on a test, do we say that it is not prime or do we show 2 solutions? So if I am going to ask for more than one solution, I will explicitly ask for that. If I just ask you what is this value, you should assume that there is only one answer, and if there's more than one answer, it's not well defined for the purposes of division. Okay, so let's take a, so let's take a 5-minute break and be back at 10. And so I actually had 3 sections I was hoping to get through today. I may not end up getting through all 3 sections, but that's all right. So let's take a quick break and I'll see you back in about at 10 o'clock.